Hey everybody, welcome back to the Unreal Engine live stream. We just had to drop out and drop back in because we thought we were having some audio issues. We're going to keep running with it and try to work our way out. I'm so sorry that we had to restart that. But hi again. I'm your host, Alexander Pascal, and joining me today is David Hill. He's our principal mathematician here at Epic Games, and he's going to be talking about what he's done with Convolution and Bloom in Unreal Engine. So let's hop back into it and get into the slides again. I'm so sorry for interrupting.
All right, well, let's just cut to some slides. If there's an audio delay, probably nobody will notice. The slides are pretty static. So this is just the first slide I have. It shows off a couple instances of Bloom, and only the ones on the left-hand side are using this new convolution Bloom. The one on the right-hand side is using our older style of Bloom. You see it's much less detailed, although it's quite fine. I guess the other thing I'll mention is that one of these instances of Bloom is using art I have generated, and I'll let you guess which one that might be. All right, so with the Bloom itself, why are we doing this? What's our motivation? So the belief is that a convincing Bloom really has some real impact, even if it's subtle. Just the physically motivated, the sort of physicality of it, just makes every image a little bit more believable. So what I wanted to do is adapt an offline technique that's used in film in post-processing, but for real time. And what does this really do? I also wanted to provide the ability to be able to customize some of the response too, so that you can use your own different camera responses to generate your own Bloom effects, so to make a system instead of just an effect. And my target here is really just the sort of high-end hardware and cinematics. Of course, today's high-end hardware is tomorrow's middle-end hardware, and the future's low-end hardware.
Absolutely.
So this is a feature that should become more and more available as technology progresses. So what is Bloom? On those cover images, you saw some bright stars, and you saw some bleeding of the brighter images on the screen. What you can think of Bloom is really just a form of weak scattering. So maybe some haze or a car windshield, or when you squint a little bit and looking at the sun, diffraction from your eyelashes, or if it's more cinematic, inner camera effects. And a lot of this goes under a broader category, this Fraunhofer diffraction. And I put a few references here in case you want to learn a little bit more about that. But that's really a study of so the aperture size and shape, as well as some sorts of occluders before that, and what that does to, say, a bright point of light that comes through. How is that slightly distorted or diffracted? But when I say weak scattering, what I really mean is very weak. Most light comes in and isn't scattered, but just a little bit spreads out. So what you see in this image, it's hard to see. It's a sharp point of light with a little bit of a star around that. So the single point of light is mostly focused, but a little bit has been scattered into the star shape. You'll see a lot of this if you look at photographs, like astronomical photographs of stars. Real stars in outer space don't have little cross shapes on them. That's more of an effect of our camera or our lenses. But if we're doing Bloom as weak scattering, we're making some modeling assumptions. We're going to assume that every point of light is scattered the same way. So anywhere, any pixel on your screen experiences the same sort of scattering. But for most sources, they're so faint that the amount of light that they scatter away from their single center point is just teeny. It's really imperceptible. And it's only those really, really bright sources that scatter enough light for you to be able to see that as Bloom. So that's the modeling assumption, that every point is really treated the same way, but it's bright ones that have a perceptible effect. Now, I'll talk for a minute about the standard game style Bloom. And that's what you'll use in Unreal Engine if you're using Bloom in a game, most likely. It's what we've had for quite a while. It's very fast. It has a surprising degree of flexibility. This image was generated using this original version of Bloom. The way that it works is it scatters the light as a sum of Gaussian filters. And what do I mean by that? Well, the actual process that happens within the engine is the image comes in without the Bloom. It's downsampled once, and that's the input to the Bloom. the underlying Bloom system is a single downsample. Then that downsample is taken and downsampled by half 4 additional times. Each of those new downsampled, so coarser and coarser versions of the image, has a Gaussian blur applied to it, its own Gaussian blur. So we have 5 images at 5 different resolutions, each one blurred a little bit differently. And the way those are blurred are set in the post-processing volume, and then they're summed back together. So it's very fast, but one of the things you'll notice is that the bloom isn't very detailed. You might have detail in the sense of having a hot core and then a fall off from the core, but it doesn't have any of the sort of finer features that you recognize in more realistic or photographic blooms. But what's really happening here is each little point of light is spreading out some of its intensity just in the form of a Gaussian. So I've actually written here the formula for a Gaussian, and they're all being summed up. And that's really what we're mathematically approximating with our various downsample passes, and then we use separable blur passes. But it's very fast and it's very flexible. But we want to introduce something that was more cinematic. So for that, instead of a very symmetric bloom, we want to use something that's not a Gaussian, not circular the same way, but is actually the response of, say, a camera to a very, very bright pixel. So that's what I'm showing right here. This is camera scattering a single point of light. And on the leftmost part of the slide, you'll see a close-up. Well, you'll see just the full image. This is just a camera having taken a picture of a single point. And it makes this little star shape. You can barely see the star shape. If you zoom in on it, what you see in the center is you see there's actually a lot of rich detail right around that center. The very center of the pixel is more than 10,000 times brighter than any other part of the screen. So that shows you how weak this scattering really is. Almost all of that light just stayed right in the very center, but enough of it scattered out that you can see it. And if I actually adjust the contrast of the image, so the rightmost image is the same as the left, but with the image contrast adjusted, you see that information really is scattered over a wide range of that initial photograph. But if you were to measure the intensity of the center, it'd be over 10,000, and the other points you can still see on the screen as illuminated are far, far less than 1. So that gives you a sense of just the extreme drop-off. But this is an example of what happens with bloom if you just have a camera taking a picture of a bright point. So what we really want to do is we want to treat every image, every pixel on the screen as a potential source for, or as a real source for scatter. So every single point on the screen is a little pixel, and it's going to spread its brightness to all of its neighbors. So here's where we're going to start doing a little bit of mathematics, and I'm going to try to actually demystify it a little bit. So we're using
just a little.
Oh, sure, just a
little.
Just a little.
It seems like so much.
I can't demystify it too much because then I'd lose my license as a mathematician. But so what you see at the top is it in its most complex form, and then by the bottom of the slide, it's going to seem pretty simple. So you can see this scatter. Any scatter operation you can recast as a gather operation. So the brightness of a pixel, well, that's the sum of all the light that gets scattered into that pixel. So I gather it, I draw it into me, plus the amount I retain after I've scattered my 10% away to my neighbors. So that on the top of the slide, you see a filtered value, and then a little bit of mathematical mysticism. That's what they call it. In mathematics, you'll see that written as a convolution, this V star F. V is my original signal, it's my image, F is my filter, and that filter in our case is something like this Bloom kernel. It's what each pixel, the way each pixel shares its information with its neighbors. And then in a continuous sense version, it's just, for us, a double integral of grabbing data from all of my neighbors weighted appropriately by this filter, by this response to a single bright pixel. But, all right, so that's an integral, but we're going to do things computationally, and that generally means integrals become sums. So if you look a little bit lower down, you see what we really have just in one dimension. It's really just a weighted sum of gathering values from its neighbors. So for example, in the very simple case, if I say, instead of my complicated star shape defining my weights, and that's really what this Bloom kernel, this response, this filter is, it's a set of weights. So instead of that complicated star, if I had a very simple set of weights that just said, for a given pixel, I want to get a quarter of my neighbor on my left, and a quarter on my neighbor of my right, and a half of me, and that's going to be the output, that would just be a nice smoothing filter. And you can see how that would be smoothing. It would be mostly the original input value at the center, plus a little bit from its neighbors. So that's, when you hear the term convolution, what I really want you to think is this is just a fancy way to say a weighted sum where the weights are some sort of complicated distribution. But that's all it really is it's a weighted sum. So it allows us, for every pixel on the screen, to gather information from all the other pixels according to this response, according to this sort of response kernel. So, so that's what a convolution is. It's this weighted sum. But here's the problem with it. If for a given pixel, he has to gather information from all the other pixels on the screen. They're all going to contribute. They're all going to spread some light in this weak scattering. So each single pixel has to gather from all the other pixels. And when you think about that at first, that's an order n squared operation. I have n pixels, and for each one I have to do n gathers. So now I have n squared. That seems pretty crummy.
It's very heavy sounding.
Yeah, so that's super heavy sounding. That's what we don't want. So that's a very bad scaling. So we need a faster way. And it turns out that a faster way to do this convolution is this fast Fourier transform, FFT. And I'll go into a little bit of detail about that. But our motivation in using this technique, this sort of mathematical apparatus of a fast Fourier transform, is we want to gather data. We want to gather all the light that's scattered for each pixel on the screen as efficiently as we can. So the fast Fourier transform allows us to do that. And here's sort of the underlying mechanism. A Fourier transform is something that takes a signal. In this case, it's an image. But it could be a sound signal. It could be anything. A signal of data coming in, and it transforms that into a system, amplitudes for frequencies. So you've heard of a high-pass filter or a low-pass filter. What a Fourier transform does is it takes your original signal, it turns it into frequencies. They call that going to frequency space. It's really turning things into a sum of sine waves. And each sine wave has its own frequency, and each sine wave has its own amplitude. So it's turning it into a series of sine waves. They each have individual amplitudes, and the higher frequency ones, if you have a low-pass filter, you kill off. The low-frequency ones, if you have a high-pass filter, you kill off. But that's Fourier transform takes data and turns it into frequency information. So to do a convolution, it turns out the way you do it is you take your image, you take your signal, you transform it into this special frequency space. You do the same thing with the filter, our little star shape. You simply multiply their frequency amplitudes together, and then you inverse transform the result of that. Now I know these are just words at this point, but this is the sort of sequence that we'll go through. We'll take an image, we'll turn it into frequency data, we do the same thing with the filter, we multiply them, and then when we come back, we end up with something a bit more interesting, like this picture of the car. We've got this pretty cool looking Camaro, but it could look cooler. We transform it along with this filter, we'll call it a kernel, and then we multiply and transform back, and suddenly the hot little spots in the car now bloom out for us. And you can see even there, they're like the little star blooms, but there are also some other brightness.
And then right on the wheel too, on the rim.
Yeah, you can definitely see it on the rim.
Where the highest reflectivity is.
The spec, it really picks up the spec hits. Those are very high intensity. But it's harder to see in this image, but when we play around with the editor a little later, you'll see that not only does it do these nice spec hit blooms, but the more broader, emissive, glowy bloom. Yeah. You can see a little bit of it around the headlights here, but that's not really what's being showed off.
Before we go to the next slide, chat's actually, a few people on YouTube chat in a couple of places would just and this seems like the kind of brief high level of what's happening behind the scenes. So just to kind of go over a quick summary, and I guess more layman's terms, what we're doing is we take whatever we're rendering, we see the highest peaks of brightness, we let those kind of pull themselves together like a, that's like a streak of brightness where the white hits, but we pull it together into the most central point, and then based on how bright that is, you amplify the size of that starburst effect.
Well, that would be one way to do it. But what we do is actually more automatic than that.
Oh, wow.
So what we're doing is we take the image, and that image, every pixel has an intensity, and we don't discriminate against low intensity or high intensity. Our filter essentially does that for us.
So there's like tons of little tiny ones you can't even see?
One way you could think about it is every pixel on the screen turns into a teeny star shape. And if you have a very bright pixel, that star shape, the contrast, it's like when we play with the contrast of that star shape. We go back here, this image on the right shows that star shape, but where I played with the contrast, and you see it's actually a much bigger star than you'd imagine. So if the pixel's pretty bright, it spreads its energy out, and you can see more of that star. So every pixel makes its own little star on the screen, but most of them are so faint that you can't see the radial lines from it.
That makes sense then. Okay, I see what you're saying.
So that's really what this convolution or this weighted sum is each pixel is making one of these little stars, and I'm just gathering, at a single pixel, I'm gathering the star, the spread out from all the each of its neighbor pixels, or all the other pixels really on the screen.
Okay, I see now.
So you can either think of it as each pixel making a little star, or you can think of it as, I'm a pixel, I know all the others are going to spread out light, I'm just going to collect all of their light. So that's all this is doing, is it's saying for a given pixel, I want to just collect the amount that's being broadcast by every other pixel, and that's going to be my intensity when I'm done. But it's just as easy to think of it as saying every pixel on the screen makes a little colored version of this star, but for the most part they're so faint, the radial parts are so faint you just don't see it. And if I have a bunch of bright pixels right next to each other, well, then they all make these little stars, and they'll start to blend together to look more like a smoother bloom shape.
All right.
So that's why how you can get these more emissive, big glowy things that don't look like stars, but they really are just the composition of a lot of them next to each other.
That's very cool.
So that's the magic of it, is that we don't have to ask how bright is each pixel, that the system basically is agnostic to that, and it scatters light for each pixel, and it's only the ones that were bright that you see at the end as having bloomed.
All right. Thank you so much for clarifying.
Oh, no, it's a weird sort of thing, isn't it?
Yeah, if you think about it, it's almost like the most crazy way you could go about rendering. So we look at every single pixel, and we evaluate every single pixel all at once.
Yeah, so that's the underlying idea behind just the model of the way the camera responds to a single bright point. Well, it responds to every point that same way. Only you don't get to see the bloom aspect of it, because most points, most places, when I'm taking a picture, almost all the light coming in is so faint that you don't get to see how it's bloomed out. But if I could increase the brightness of every pixel coming in, each of them would be making one of these little bright stars. So we're trying to treat each pixel equally and let it bloom according to its own merits.
Yeah, that's very cool.
So that's the underlying bit of it, and that makes it work really well. It also makes it more expensive, and that's why we have to go through this process of involving this mathematical apparatus of Fourier transforms. So the Fourier transforms, so I said, are used to take the image data, convert it to frequencies, we multiply there, and then we convert it back to image data. And the savings happens because the Fourier transforms, it turns out, are n log n. So you remember the original way we could have done this, if we'd been more naive, would have been an n squared operation. But if we go this route, if we use this apparatus, it's actually n log n, so that's something that scales much better. It's much closer to linear scaling in the number of pixels you have, as opposed to quadratic scaling in your number of pixels. So when we transform from signal to frequencies, it's fairly quick. Multiply, which is virtually free, and then transform back. So what is a Fourier transform? All right, now I promise it's only a little more math, and then we'll actually bust open the editor and do some cool stuff.
Oh, awesome.
But this can be kind of fun. I think so.
That's why you became a principal mathematician.
That's right.
That's a very cool career choice. I just wanted to say, like, I don't know a lot of people who professionally went into mathematics, but it's awesome that this is what you get to do with that.
Yes, this is very fun. I went into math originally, and this is the most fun I've had using it. Other applications were much less enjoyable.
Do you get to tell like your other mathematician friends, like, oh, well, I mean, I work in video games now, you know?
Yeah, I do, and they're jealous, and their kids are especially jealous.
Oh, that's awesome.
So that part's pretty good. So this is what a Fourier transform is. I have a signal that's just, I've recorded values somewhere equally spaced, think pixels, and I can actually represent it as a sum of sine and cosine waves. And when you look here, you don't first see sine and cosine waves. You see some other notation. And I have to apologize, that's sort of a compact notation that mathematicians used for sines and cosines. It's this complex exponential. But V sub n, little n, that's our input signal. Capital V sub k, that's the amplitude for each sine and cosine frequency. And then there's this exponential, which is really just a compact way of writing sines plus cosines. So this is saying my signal can be represented in terms of sines and cosines. And then the formula on the bottom says, how do I compute the amplitudes of the individual sines and cosines? I have to do some other sum to get these. And then I've included this image. And this image doesn't look, it's not a computer graphics image. It's not particularly appealing. It's not a car, it's not a monster. It's a line plot. But what this is showing, and I thought it was kind of fun, is just a low-pass filter. In blue, I have some original signal I generated using random numbers and sine waves. And then I've decomposed it into its frequencies, and I've thrown away the highest frequencies and plotted that as the sort of gold curve on there. That follows the blue curve. And what I've really done is I've just done a low-pass filter. I could have fully recreated that signal by adding all of my sine functions together. But I wanted to show that you can filter a signal using Fourier transforms. That's what signal processing people do all the time. So that's just some token math. So that what I want you to see here, those of you who are still watching, is that there's a way to compute these coefficients from your signal. These coefficients are amplitudes. Think of them as amplitudes for sines and cosine waves. And again, this doesn't look like an n log n problem. I'll just hint at what makes this a fast Fourier transform instead of just a Fourier transform. So you'll hear people use these terms interchangeably. They'll just say FFT, and that stands for fast Fourier transform.
I didn't even know what it, I went through all the release notes, and I didn't even
well, so that's
what that is.
So the Fourier transforms decompose a signal into sine and cosine waves, and the fast part is an algorithm that lets you do that more quickly than you might first think you can do. So underlying way it works, I encourage people who are interested in this to go to something like Wikipedia or other places to really learn about it, because I'm just going to give you a little motivation. You've got a sum to do. It's a sum of sine and cosines. Sines and cosines inherently have a lot of symmetry to them. So it turns out you can split your original sum into a sum of the even terms and a sum of the odd terms. And then when you look at it the special way, you see that, oh, if I compute the first half of the coefficients, I only have to do a little bit of work to also compute the second half of the coefficients. I can basically get the second half of my amplitudes, my frequency amplitudes, for free. And that's the key observation that allows somebody to make a fast Fourier transform, that I have input data, and I'm going to do a full transform, but if I only look at the even terms separately from the odd terms, I can save some time. And then after you see that, you do what computer scientists do all the time, which is they make it recursive. They say, oh, I split my work in half, I can do it again. Split those halves in half, I can split those halves in half, and then descend all the way until they have a very simple problem to do. So that's really where that n log n part comes from, is that you keep splitting things, decomposing things into odd and even parts of a sum, and recognizing symmetry that you can exploit. So I just want to give you a little bit of motivation. So Fourier transforms decomposing into frequencies. Fast Fourier transform is something that exploits the symmetries of the underlying sines and cosines to let you do it more quickly than you think you ought to be able to. But that's enough of that. So to actually do this in the Unreal Engine, we wanted to do it in a performant way that would allow you to do this on high-end graphics cards or for cinematics. That meant really doing it on the GPU. And GPUs are highly parallel. They've got sort of funny thread communication limitations. It turns out there are similar restrictions in this parallel processing on GPUs as there are in supercomputing architectures. Each node of a supercomputer can be blazingly fast, but when they have to talk to each other, it slows down a lot. So in the world of supercomputing, this problem's already been tackled: how best to parallelize fast Fourier transform across multiple nodes. And there's a special formulation, and it does what we were just talking about. It exploits all these different symmetries in that same sum, but allows you to break it into parts where different threads or different processors can work on it. That's the Stockham formulation. It was used in vector computers in the 80s, and about 9-10 years ago, it was first applied successfully to GPUs, also in the supercomputing range. And our implementation really follows pretty closely this application to GPUs of the Stockholm formulation. And under the hood, for those of you who are interested in compute shaders, each scan line in an image is transformed independently. It transforms a scan line, a scan line, a scan line, and each scan line is managed by a thread group. And within a thread group, there's group shared memory, so it can trade off information. So that's sort of the gist of it. If you actually are a little more curious, there are some what I've done is implement this in compute shaders. And the way that we do this Bloom convolution is it breaks into 3 different passes or dispatches of compute shaders. The first pass transforms the whole image in, let's say, the horizontal direction, and it uses a special trick that lets you get away with transforming 2 signals, red and green, as one signal, and blue and alpha as another signal. And then we transform it in the vertical direction, do our convolution, transform back in the vertical direction in the second pass. And the third pass, we invert the horizontal transform. So this is the first time you hear me saying things like horizontal and vertical transforms. And that's really because I didn't want to make it any more complicated than it had to be. So the Fourier transform we talked about earlier is a 1D creature. If you want to transform a 2D image, you do a 1D transform in X, and then you do a 1D transform in Y. So there's really not too much more to it there. But for people who are interested in signal processing, there are plenty of opportunities for them to learn more about how that works. So this is under the hood what we have. When we're doing our convolution, we really fire off 3 compute shade dispatches, something that transforms the image in one direction, something that transforms in the other direction to get me fully in frequency space, does a convolution, transforms back, then a final pass to transform back into the image. So the image you see at the end isn't the image that you started with. It's a new image that's been made by this full process. All right, so for those of you who stuck with us, we can now cut to the fun bits.
And I'm sure that we're getting plenty of questions. Right. We're going to save those to the very end here, but people. The reaction has actually been pretty interesting because we have a lot of people out there that are very into the heavy maths, and then people that are just like, "This is amazing! It's so great to see that someone who knows what he's doing is really in there deep." So it's good to see that this is actually a lot of back end work that we don't always get to show off on the streams, so it's really good that we get to show all this. But yeah, I'm really excited to show off the practical application, which is probably going to be the shortest part because it's so easy to use.
This will be, you're right. It's pretty simple. So what I have here is just a little bit of the Paragon art. and there's some statue, some tower.
Yeah, it's actually, is it just a tower or is it one of the like main ones? Clint actually plays a lot of Paragon.
Okay.
That's just a tower.
This is just a regular tower?
All right. Well, this is an incredibly cool tower because it's covered with all this bright emissive stuff. So right now it's my favorite tower. And what we see, we're currently using the sort of game version of Bloom, the standard version of Bloom. And I'll try not to be too twitchy with the mouse, but you can see the standard version of the Bloom, these blue emissives appear to glow. They extend beyond their boundaries, but in a pretty simple shape. I mean, it looks nice. It looks pretty awesome. But here I have a post-process volume over on the right-hand side, and it's set to this standard sum of Gaussians method for Bloom. I'll cover the new options, the new controls in the post-process in a moment, but let me just switch this over from the standard to the convolution. So now, here we're seeing the convolution version of the Bloom with the same emissives, and you can see a lot more sort of rich detail. Around this large blue glowy bit, it's still a very soft glow, but these smaller emissive areas that have sharp corners, well, you can see a lot more of this sort of fine detail that arises from the underlying asymmetries in our Bloom response, in our Bloom kernel. So that makes it look pretty cool. Let's see.
It's very nice.
And it, it affects, here we can see the sun sort of peeking through a little bit, and now you see some nice little...
It's actually creating a starbursting like around that corner.
That's right. It's doing a starburst on the sun too. If we just go back to our old version of the Bloom, it's nice. It's a nice circular, very symmetric, but
it doesn't feel real.
Yeah, this gives us a little bit more. A little bit more. I can even, let's see if I can make the sun shine through the trees a little bit. I don't know how well this comes out across everywhere else, but in here you can see the nice little star shapes coming through poking through the trees. That's probably too small a detail to be able to see well at home, but trust me, it looks awesome. It's just nice to sort of play peekaboo with it. Let's see, there's some other little features on this other tower. Yeah, you can see
that's really obvious right
like
there.
It is. And again, we can make it go away.
I see the major difference.
Sure, I'm back on the right post-process volume. Flip.
And you said it's important this is your global post-process volume that you're controlling this on, of course.
That's right.
Would this work within a volume? Like if I just had
sure.
Okay, so if I stepped into one area, this could be kicked on for a moment.
That's right. This right now I'm in a post-process volume that I myself dropped in here and set to be unbounded for simplicity's sake, but it just lives within a post-process volume. All right. Let's see. If we can get a little closer. Oh, I'm too twitchy with this.
if you scroll down on the mouse wheel, it'll slow down the speed of which you fly through the world.
Okay.
And also, if you hold both buttons down, you can kind of drift around a little. There you go.
There we go. Yeah. So I'm much better at typing.
I know some Blender users that never touch the mouse. Oh yeah. Yeah. There's some people out there that just don't mouse very well.
Yeah. Yeah. I'm a bad mouse.
That's all right. You're amazing at math. That's all that matters.
That's right. So here you can also see, again, it is capable of giving this sort of soft bloom, this sort of, this radiance, but that's a reflection of how uniform the emissive is, how uniform that source of light is. Of course, it works with anything that generates a high intensity pixel, whether it's a specular hit on the car or an emissive like this. But
can we also hit F11 and do the full screen thing just to show it off?
Sure. There we are.
There, yeah. Oh, you can really see it down at the bottom there too, where there's the streaks coming out there.
Yeah. Oh, that looks awesome. I can pull back a little, and you can see these guys.
Wow, so intense.
Now let's try this sun through the leaves again.
Yeah.
There, you can see some of it. It's not quite as.
So there you go, peeking between the different leaves.
Yeah.
Yeah. So and then as the cloud moves over it too, it's kind of changing the amount of intensity. That's why it's...
That's right. Yeah, you can see that cloud to include things. And
Yeah, this is video games these days. Like, this is what we're talking about. Like, sometimes I have to stand back and be like, yeah, this isn't just pixel art anymore.
It makes me think about lying on my back as a kid and staring through the leaves of a tree. So clearly I'm not an artist, but I really appreciate the stuff that they've been able to generate.
Oh, you're an artist in your own way.
Oh, thank you.
In fact, all of chat seems to believe that you are Bob Ross of math. So.
Well, that's all right.
Yeah, we're liking that. That's good.
I'll wear that with pride. In the absence of other evidence, I'll take it in the best possible light. Yeah. What else was I going to say about this? I was going to go back to showing you the controls a little bit so you have a sense of what the options are and how to play with this yourself. So in the Bloom post-process setting, so under Lens, there's Bloom, and under Bloom, we now have a method option, and it switches between standard, which is the original version of Bloom.
Mm-hmm.
It uses a bunch of parameters that really, under the hood, are telling you how to do these different Gaussian blurs that get added back together. So you can have standard, or you can have the convolution version. Now, if you have the convolution version, you'll be given the option of providing it a kernel. And that's just the response of the camera to a bright light.
You've amazingly timed this just as someone in chat asked, oh, how do I change the kernel out, and can I change the kernel out?
You can change the kernel out, which is awesome, because we provide one kernel. It'll be a default kernel, so you don't have to place one here. But if you want to, you can make your own. This is the default kernel. If I change the exposure, you can see that there's lots of stuff there. It's just not that visible. If you want to make your own kernel, please center it. You want the center of the kernel to be the center of your texture. And you want the very center of the kernel to be much, much brighter than the rest of the kernel. The percentage of energy that's in that center of your kernel, of your image, is basically how sharp your image is going to be afterwards. If your kernel is something that's very soft and very smooth and has a very low center, if the intensity is pretty low there, it's as if your camera was pretty crummy and you have lots of blur. So the camera, this is a filter. Every filter introduces a teeny bit of blur. The way you control that blur is you make the center of your kernel incredibly hot.
Mm-hmm.
So here it's like 10 or 60,000, and everywhere else is 1 or less. So this is an EXR. You want to make an EXR to have the range that you need. You'll find in our release documentations, as well as our other documents, that there are two things you need to do. One, you need to set this to have no MIP maps, and the other thing, never stream. And the reasons for this is that this kernel is being used for your compositing, and if you have MIP maps, you might not get this kernel. You'll get a much lower resolution version of this. And then when you've processed your image with it, you'll get something that is unexpectedly bad. And the same thing with never stream. If you allow this to stream in, if the texture streamer is overloaded and it's dumped this texture and it hasn't brought one back in, then again, because you're processing the full image by basically multiplying this in everywhere, if this isn't present and it gives you something default, again, you've got garbage.
No, that's
so these things are
not good.
These two things are very important.
All right.
That's explicitly stated in our documentation, and it's something that you'll want to do. But you can bring in your own kernel. You just put it right here. If this kernel is missing, it'll use our default kernel. You can get to that in the engine base INI. It tells you where the default kernel lives, if you feel like spelunking. And now this actually has a few options, and I'll tell you what these options are. Like this one I'll ignore for a moment. The main option, the one you'll be most interested in, is called Convolution Boost.
Mm-hmm. Can we get rid of the picture-in-picture and go a little bit bigger there, Clint? Thanks.
Okay. I can drag this.
Oh, it was just because our picture-in-picture was overlapping what you were doing. I didn't want to get it in the way.
So I'm using an old build of the engine right now, and I think the tooltip isn't showing up the way it should. So I'll tell you what these options are. But in your copy of UE4, you should have a pretty useful tooltip, as well as the documentation. What Convolution Boost does is it takes the input image before it's post-processed by Bloom, and it will increase the intensity of bright pixels. So much of our graphics pipeline is designed to sort of suppress incredibly bright sort of firefly pixels that appear and disappear, that we need to actually give you a way to promote some bright pixels. If some pixel's kind of bright, but I want to increase its intensity a bunch more, this is where you do it. So this says every pixel whose luminance is greater than 4 and less than, I've put in this number, 20,000, go ahead and multiply it up by a factor. Now, you don't really see much of a result anywhere other than our points that are being bloomed, because this intensity, this brightness of this pixel, is somebody who's going to be crushed by their tone mapper later. So I'm basically exploiting the fact that we have some if I have a bright pixel whose intensity is 4 before it hits the system, I know that when the tone mapper takes care of it, it's going to be put somewhere else. It's going to be crushed.
Because there's no reason to try to boost that.
That's right.
Yeah.
So I can boost 4 to 40,000 and you won't know the difference. But the bloom post-processing will. So this allows you to basically amplify bright pixels, and the effect that has is there. Now I'm not amplifying it, or here I'm amplifying it a little bit, or I'm going to amplify it a lot. It allows you to set this amplification in here for the bright pixels so that they have more energy to scatter to all the other pixels on the screen. So that is the convolution boost, and it's probably the control you will be most interested in.
Yep.
It's set to some defaults that are pretty good, that work well with the kernel we provide. Now here's another control. This one's kind of funny. So this kernel, you'll provide a kernel, is the response of a camera to a single bright light. And it's not exactly centered. It's pretty centered. The center of this is almost at the middle of the screen. But if you bring one in and it's not centered at all, you can tell me where the center is with this convolution center UV. So it shouldn't be way over here, but generally it's around 0.5 and say 0.5. But if you move these values around, you'll actually be able to shift your output image. And that's a reflection of the fact that the image that's being generated here is a fully filtered version of the original image. I'm not adding something to the original image. I'm not drawing stars, taking the original image and just drawing some stars on it. I'm taking the original image, putting it in this weird space, multiplying it with something else, then converting it back to an image for you. So that's why this convolution center can actually move things. It's as if you could also interpret this as saying, where's the center of my input image? So if I say the center was over here, oops. If I say
it was a 0.5 point something. So you have to only one decimal place at a time with the floats.
So you see I can move it.
Just a slight adjustment makes a huge difference.
It does, because then it interprets the center of where it believes the center of my original bloom kernel was. Usually you'll find a setting that you like, and it'll be consistent with the kernel that you've made, and then you'll just stick with it and you're fine. So it's not something I expect you to animate or really play with. Now there's one more control that was added, and it's something that you generally won't have to touch at all, I hope. It's this convolution buffer. So what happens when the underlying mathematics for this sort of bloom assumes that everything is periodic, everything's made out of sine and cosine waves. So what it really assumes here is I have periodic copies of this image. And I could potentially have some bright image on the edge of my picture show up, bloom over on the other edge, which would be horrible, which wouldn't be what you want. So this convolution buffer secretly puts some black space around your input image. So if data blooms out a little bit on one side, it doesn't wrap around and bloom in on the other side. The mathematically correct value to have here would be 1. It would keep anything from blooming, a super bright pixel that could bloom across the whole screen to wrap around. But the mathematically correct version is not the most performant number you want here. Because that makes it a much larger image that I'm really processing. So I'm actually processing this image plus a black border. And if I make the black border very large, it costs more. And we have that n log n scaling, and I want to make n as small as possible. So generally you won't have to have to fidget with this number either. I've set it to a number that, well, I won't go into the details. The default should be fine in almost every case, but a few situations where you've constructed something really interesting for your cinematic that blooms across the whole screen, if you see any periodicity artifacts, then you can increase this and pay a performance penalty. But it's like, how do I want to say it? It's a recognition that computer graphics is the art of cheating.
Yeah, yeah.
So I'm giving you the ability to cheat.
I actually had a game development professor once tell me you'll never get anywhere in life cheating, and I was like,
that's
what? This is game development. That's all we do is cheat.
Computer graphics is all about finding the most efficient way to, we're saving some out-of-date packages.
Oh,
the most efficient way to do something that's plausible and as physically correct as you can within constraints.
Awesome.
So those are really the things I wanted to show. And I'm looking forward to seeing what people will do in playing with it. Are there
yes.
questions
I think we definitely should cover some of these questions here for sure. Right. So these kind of run the gambit of very high level to very low level of questions. I think there was a little bit of something that we should clarify here, because people are asking, could this be used to make fast blur effects? Could this be used to make fast this and that and quick versions of things? But this is really for cinematics.
It's more for cinematics and for high-end hardware.
Mm-hmm.
I mean, I could flippantly say it could be used to make slow things, but but I don't really want it to. That's not really fair to it either.
No.
It's really designed to give you a higher degree of realism, and you do have to pay a little bit for that. It's unfortunately, it's that no free lunch.
Yeah.
Like, I want to pay as little for lunch as possible, but there's no free lunch.
Mm-hmm. And this definitely, because you're processing every single pixel on the screen,
right.
This is not a VR friendly thing to do, because that's doubling the process.
That's right. You wouldn't use this for VR. Unfortunately, as much as I love VR, you can use it to do other sorts of image processing things where you have your own filter. So you could replace that kernel with something that's a mathematical filter that you're interested in and play with it. While we're advertising it as a Bloom feature, and that's really what it's designed around, it is more generally an image processing tool. I guess there's one other thing I would like to mention along those lines.
Mm-hmm.
So we really have 4 images. We've got a red image, a blue image, a green image, and an alpha image. And each of those 4 images is being processed by its own filter. So that our Bloom kernel, our little star shape, is really 4 little star shapes. We could strip away, we could look at the red, the blue, the green, and so on. So if you make your own kernel, your own image, you can't just make an image that's red or one that's blue. You need to have data in all 4 channels for this, because each channel is processed independently of the other channels. So that just to sort of clarify that point.
Yeah, actually that kind of leads us into some questions. A lot of people are very curious about kernels. So when you were kind of showing off the things that how you as a developer will be interacting with it, they were very curious about how heavy the kernel is, depending on like the size of the image. Does it always have to stay the same image size? Is there any way to accidentally make it too heavy? Is there?
No, I can tell you.
And Awesome Aller asks, can I use my face as a kernel?
Yes, you can. You can totally use your face as a kernel.
That's good.
Shrink it down so it's pretty small, so everything is really focused around your face, like that Bloom trend. And put a bright spot in the center of it, but you can totally use that. You can use pretty much any image you want, but you should make sure that it's fairly compact, or at least most of the intensity of it is very compact.
Awesome.
But what was the other part of it?
Is there a way to accidentally make it
too heavy?
Too heavy. Like, actually, it might be a good example to just say, like, if you know of a way to do it, just tell them, and then say, don't do that.
Let's see. I can tell you what is done with the kernel. The kernel, regardless of the original size of the image, it gets remapped into a size that's consistent with your buffer. And then it gets transformed into this frequency space where we can do our convolution, and that gets cached. So we only have to transform the kernel when you change your kernel, change your viewport size, or a few other things like that. Otherwise, it gets right-sized to the image, transformed, and then the transformed version is cached, so that we'd have to do less computation. So can you make one that's too heavy? It is being streamed in, and you are keeping it there. So yes, you could. It doesn't make sense to make one at a higher resolution than anything you intend to ever display. So that if you make one that's like 4K or 8K, and you're never going to be bigger than like 1028 or
yeah, you would never be able to get that out of it.
Yeah, so it doesn't have to be incredibly sharp. You do want to make sure it's going to be at a resolution that's equal to or greater than your viewport resolution.
Oh, that's
but it doesn't have to be. It doesn't have to be ridiculously high resolution.
All right, that's good. Let's see here. Do we have any new nodes in the material editor or any of the other editors that we should be aware of that will affect this?
Not that. No. This is really
it's
isolated
purely in this.
In the post-processing volume.
All right. Let's see here. They were asking for a couple of other things. They're a little off topic. I'm trying to stay just within the topic of this here today. Let's see. Is there any way to limit it for better precision? And I guess you did kind of go over like how to kind of clamp the high and the low end of things on your kernel. So
that's right.
We did get to go into some of that. Let's see. We do have a question that I saw in here. Do you know about wavelet by any chance?
It's a different sort of transform and compression.
Yeah, someone, Jen was asking, isn't wavelet a much cooler version of like Fourier or a different?
So Fourier transforms will take a signal and of a certain length, and then re-represent that signal in terms of sine and cosine waves, where all you're really getting out is the amplitude of the sine and cosine waves. So I say there's a math term, a basis, a fixed number of sine waves and cosine waves with certain harmonics. A long one, half length, a quarter length, and so on. And I'm representing my signal in terms of that. Wavelets, on the other hand, try to isolate things both in frequency space and spatially. So they're related. You do have a basis. You are taking your original signal and re-expressing it in terms of coefficients and from certain sorts of functions, and you can think of that as a compression if you like. But that basis is a very different kind of beast because it's compact both in space and in frequency. It's cool.
Yeah.
I don't know enough about fast transforms for wavelets to know how applicable it would be to problems like this. So the core reason we used the FFT was that we could do this convolution. We could beat the n squared scaling and bring it down to an n log n scaling and make it, although it's not as fast as I would like it, it makes it realistic. It brought it into the range where we could do it, and fly around inside Paragon. It looks great. We can do it in our cinematics and on high-end hardware. But I can't really speak to, I don't know enough about the performance characteristics of wavelets and their scaling to tell you.
All right. Let's see. And here's something that you actually, you and I had talked about just before this, and we should probably also cover it just before we get going. But what is the difference in cost? The JHNZ was asking what is the difference in cost versus default Bloom, and could it be used in games? You did kind of mention that this isn't something you want to try to do a lot of runtime stuff on, but you and I did talk about how we can actually see the cost and where the cost is coming from. So if we want to hop back in the editor real fast, we'll just show. I'd just like to show y'all what to be looking for when you're looking for the cost here.
Okay. Actually, on the slide we have up right now, I'll show you something here, and then we'll go into the editor.
Yeah.
So on this slide, you see a little gray box on the right-hand side. It's the 3 sentences. They start with FFT. It says 2 for 1. It gives you a buffer size. It says FFT, apply, forward, transform. So these are things we're going to look for in a minute, and we're going to find them by using the profile GPU tool. And that's where I grabbed this, and that's what will give you the timing. So I would not recommend using this in game in its current form. perhaps in the future we'll have a version that'll be a little bit more game friendly. But right now this is more about high-end and cinematics tool. Let's see, so I want the window developer tool. Where's the output log? All right. So I'm going to bring up profile GPU. Okay. This is our GPU visualizer. You can use this to see what anything costs. And I know that this is in the post-processing, so I'll just drill down to it. Scene, I open up post-processing. These are all sorts of different things that are being fired off right now in the post-processing graph. And over here you see the cost, and here are our 3 steps. So you see it's pretty heavy. 0.07 milliseconds to transform forward, 0.2 milliseconds to do our convolution, and transform in the vertical direction, transform back in the vertical direction, and then 0.06 milliseconds at the end to bring us back to our final image that's going to be displayed. And then the next step is we go through the tone mapper and things like that. But in general, GPU visualizer, I got to it through using the console, the output log, and typing profile GPU. And it's a wealth of good information if you're trying to profile what you're doing to see where the cost is and where you're spending your budget. So no, I'm sorry, I wish I could say that this was super wicked awesome and would run on anything and would be great in games, but I'm not quite that good a mathematician yet. Yet. I hold out hope.
Awesome. That's very cool. So let's see here. We're getting down to a couple questions, and just because of the audio issues we had before, we might have to be done in after one more. Can you give this is actually probably a good one to leave out on. Can you just give a quick and simple summary, like what's the smallest, most compact sentence you could summarize what the feature does in?
All right. This feature allows us to do much more complicated and physically realistic looking bloom based on input that you can provide in the form of a given camera's response to a bright source of light. And it differs from game style blooms in that the results are much more detailed and sort of complicated and rich, really. I really like it.
Yeah, I think it looks fantastic. It's a great new feature for cinematics and for rendering shots.
What we're really doing is bringing over some technology and concepts from the offline and film world and making it available for us in the real-time world.
Yeah, that's a really good point. Awesome. So I think that's all the time that we have today. Thank you so much for coming out, David. It's been enlightening. I didn't mean for that to be a pun. It's been very educational. We've learned a lot today, and it was really cool. But thank you all for coming out. Yes, you might have noticed News and Community Spotlight has been moved. We're going to be sectioning that off into another section so that we don't cram everything into one stream and all that. And so that will be a pre-recorded thing later. But thank you all for coming out. We'll see you on next Tuesday when, I'm just going to throw this one out here, we currently have planned a Blender to UE4 live stream, which is something that a lot of people have been asking for. Cool. I'm very excited for it. Yeah, we're going to have, we're actually going to have someone from Blender come on, so I'm excited for this.
Awesome.
Yes. So thank you all for coming out, like I said, and like, follow, subscribe, hit all the social media things. I always have to say that because you don't want to ever miss any Unreal Engine news, and we'll see you around. So bye now.
All right. Bye.